Okay, so thanks for inviting me. I'm here to talk about LDDMM, which stands for a really long acronym that I may or may not get into later. I guess first I'll just introduce myself a little bit. My name is Calder. I'm currently a grad student in Department of Medical Biophysics at U Toronto, and I did my undergrad at U Chicago and majored in math, graduating in 2020. Great time. So yeah, I'm doing medical imaging research, particularly cardiac MRI, and I guess we're going to talk about some image registration and some powerful math. So brief outline of the talk. First, I'm going to talk about some of the theory of this registration approach. Second, I'm going to talk about how we can discretize this and solve it on a computer. And last, how I'm implementing this in code and getting some half decent results that actually may be a little bit new for at least me. They're pretty new and pretty cool. So yeah. First, a bit about the theory. So LDMM stands for Large Deformation Diffeomorphic Metric Mappings. And this talk is going to follow a paper or a PhD thesis by Thomas Polzin at Universidad zu Lübeck from 2018. And so he went over the theory, numerics, and applications. His application was mainly for lung volume imaging, although I do cardiac MRI, obviously, so I have a couple different ideas on how I want to use this. So the overall problem is this. So we have two images. We're going to call them a template image, I0, and a reference image, I1. So the template is sort of what we're scanning, and the reference is what we want it to look like. So then we take I0, warp the grid, and get this registered image, I0 after phi, which is the transformed template image. So our goal is, given these two images, warp the template image to look like the reference image. And so the insight of this thesis is to discretize, then optimize. Namely, first, you formulate the problem as a discrete numerical problem from the start, instead of starting with a continuous theory and then digitizing it at the end. So I'm going to sort of go with the latter approach. I'm going to talk about the theory first and then how we're digitizing this. But in the application of this, in this thesis, they go over sort of starting it, formulating the problem as numerics from the start. So just some quick notation for the images. So omega is, let's say, an open bounded domain in RD. And for medical imaging, D is usually 2 or 3. And a template image is a function I0 from omega to R. Maybe, let's say, L2, just to make sure it has finite energy. And same with reference image, I1 from omega to R. And again, the goal, quoted directly from the thesis, is find a reasonable transformation such that a transformed version of a template image is similar to a reference image. And that's way easier to describe in equations. So we're going to take phi to be a diffeomorphism from RD to itself, meaning infinitely differentiable, smooth transformation, everything we could ever want in a map. And it satisfies a couple of things. So first is that if we compose I0 after phi, it's going to look roughly like I1. And again, phi is diffeomorphism of the underlying space, RD. So you can think of this as like a grid warping, as opposed to actually changing the image. And so how do we find this? Well, we have to solve a constrained optimization problem. So you can think about it sort of from physics, where you have an energy equation, you want to minimize the energy. Whereas here we have an energy functional, where phi is going to be the argmin over some set A of this energy functional of phi, where the energy functional is going to be two terms. First is the distance measure between the warped I0 and I1. And the second is going to be a regularizer to make sure phi is smooth and sort of minimal norm in some sense. There's the set A is the set of sort of admissible transformations, which takes a bit of theory to describe. I guess some buzzwords would be reproducing kernel Hilbert spaces. That goes into sort of setting up this set A as well as given the underlying set omega. So we're not done yet. So we want to extend phi to be now a family of diffeomorphisms. So we model that as this function phi t comma x. So x is in omega and t is in 0 comma 1. So we have a flow where x or phi at time equals 0 is just going to be the identity map, and phi at t equals 1 is going to be really what we're looking at as our transformation phi. So if we're introducing this variable, we want to know how it behaves in time. And so we have this ODE, which should look fairly similar or fairly familiar, which is if you take the time derivative on one side and you have a velocity field on the other side, it's going to equal each other. So you can think of it as like a gradient flow of sorts. So we need to put some conditions on V to make this thing have a unique solution. And I think the one that we mentioned in the paper is being in this Sobolev space, which for those unfamiliar means you have 3 derivatives in L2 for each value of time. Now, when we do this computationally, you want to find both our grid warping phi and our velocity field v in order to better do our image registration problem shown here. So it's actually, instead of E of phi, it's going to be, our energy functional is now going to be E of phi comma v. So we have sort of 2 parameters at play here. So as I mentioned briefly, the reproducing kernel Hilbert space, you need the sort of differential operator to get started. And so here it's gamma times the identity minus alpha times d-dimensional Laplacian, all of that to the dth power. Then once you have this operator, you can get this momentum operator here, where you take in the velocity field and spit out the momentum. And then you can actually invert this and go from the momentum back to the velocity field. It's a lot of cool stuff here. I'm not going to go into a lot of the details. It gets into vaguely Euler-Lagrange equations of motion.
Question in the chat.
Oh, I can't see that. ODE involves one derivative. That's a good question. Not entirely sure the answer. Because I think, so the time derivative is on the left side, whereas we're sort of fixing time on the right side. So we need sort of, this is a function of space from omega to RD. So I think it's sort of different worlds where we're talking about differentiability in time, and then also this integrability constraint on space. I guess also if anyone has any questions, you're welcome to either unmute or just type them in the chat, just like that. Yeah. So now, given all this, we can describe sort of one energy functional. And so this is SSD, or the sum of squared distances. So the distance term is just going to be taking the point at any point x, taking the difference between I0 after phi inverse and minus I1, all of that squared, and then integrate it over omega. And then the second term, our regularizer, is going to be the norm of L times V, all of that squared. You have to integrate over space and over time. And then these 1/2 and the 1 over sigma squared allow you to sort of tune the parameters to get a better registration. So now we'll talk a little bit more, some more details on how we're going to discretize this problem. So first off, what does it even mean for a function to be diffeomorphic with an input as a discrete set, like a computer grid? So in the continuous sense, there's a theorem that gives a sufficient criterion for a sort of phi in the continuous sense to be a diffeomorphism. So for example, given some injection psi, which is C0 on the closure of omega, you need first the Jacobian determinant d phi to be det d phi to be positive for all x. And also we need that phi agrees with psi, our injection on the boundary. If this happens, then phi on the closure is a homeomorphism, and phi on the interior omega is a diffeomorphism, both on their respective images. And so if you apply a grid to omega, then computing this determinant on each grid point is easy. And it turns out that if this determinant is positive everywhere, that's good enough to guarantee injectivity of this psi. So that means we have a discrete diffeomorphism, meaning all we have to do is check that it's orientation preserving on the grid. So now remember there's 2 objects, right? The image and the velocity, the phi and the v. And actually one interesting thing they do to save memory is do it on 2 different grids. So the image grid is red, which is more finely sampled than the blue coarser grid. And the insight here is that you can sort of cheap out on the velocity grid and make it smaller and save it memory while still maintaining a good image registration. So one thing that we need, especially because this is what's called a multi-scale registration approach, meaning we're going to solve this problem at multiple different levels of resolution. So we're going to need interpolation, which is basically either upsampling, going up a resolution, or downsampling, going down a resolution. And this is written as a matrix P, although this can be very big, so you don't actually have to store every component. You can sort of do it sparsely. And higher dimensions, you can do this sort of component by component in this block diagonal matrix. So to discretize the regularizer, we need our operator L. So the main actor here is the Laplacian. So in one component, you have delta U, where U is our sort of step size or change, is going to be 1 over U squared times this matrix, which you can think about as like a second central difference matrix. And you can tell it's a second derivative because it has a 1 over U squared on the denominator. So from this matrix, you can form the full Laplacian using tensor products, where sort of in the n3 component, tensor n2 component, tensor delta in the n1 component, and then add the rest of them. Note that these are superscripts, not exponentials here. It confused me the first time I saw it too. And then from here, you can, that's in the way, but we can make our discrete regularizer by, well, taking the discretization of the identity map to be the identity matrix, and then we can take the discretization of the Laplacian to be our delta here, and then that's just going to be a matrix in Mn of R. So yeah, again, in momentum, we can take this discretized L, do our LTL inverse on the momentum, and then get our velocity back as well. Although we may have to apply a interpolation on this to get it to the right resolution. And then finally, you can note here that take LTL inverse is A inverse is, we call it K. That's the kernel of the reproducing kernel Hilbert space that underlies sort of this whole theory. You think of this sort of kernel as like a generalization of convolution, although it gets a little bit hairy. Yeah. So from here, we're actually not going to use sum of squared distance because it's actually a better idea to sort of look at the gradients and the changes instead of just the actual pixel values. So sort of NGF, normalized gradient fraction, or something called normalized gradient field. I'll give an analogy from linear algebra, where if you have two vectors in, I don't know, R3, RD, whatever you want, how you find the angle between them is by doing U dot V over the norm of U times the norm of V, just by U dot V equals UV cos theta, basically. And so this is sort of a generalization of that, where we're taking the inner product of gradient A, gradient B on top, and the norm of gradient A and the norm of gradient B below. And so this is sort of a fancy cosine theta. So if the gradients are parallel, it means that cosine theta is 1, which means that this whole thing is 0, meaning that A and B are going to be close to each other. If they're perpendicular, then A dot or U dot V, with the gradient inner product is going to be 0. So it's integral 1 minus 0 is going to be 1 is farther away. So yes, this does make sense as a metric. Although this inner product is actually not an inner product, it's a little bit special, where we do our usual sum of components, but then we want to add this eta squared term basically as a cutoff parameter of where is the noise gradients and where is the signal gradients. From here, well, the gradient matrix itself is similar to our Laplacian up here, but instead it's a first derivative because it only has one step size in the denominator. And also it's a more simple matrix structure. And then this term you can call a residual. And we can write this residual pretty succinctly using this sort of GI A notation, where basically we take the ith component of the gradient applied to the image, and then the next component to be eta, and take that transpose to be our vector here. And then from here, it goes into Runge-Kutta numerical optimization land, which I'm really not that good at. So for anyone who's really interested in algorithms, you can stare at this algorithm and nod along. For me, I'd rather start implementing it and doing some code. So I think we'll move on if there's no in-depth questions about this part. Get some water quickly. Got tree pollen over here in Toronto. It's crazy. Okay. So what now? Now we get to do some fun Python coding. And the best part is that I didn't even have to do any of the coding because it's already written for me by this guy named Ryo Ito. It's on GitHub. You can go look it up. Although it took me an hour and a half of debugging to make this work. So I really wouldn't recommend that. And I'll give you good links at the end for where to look at this code if you're interested. So this is LDDMM registration, although it's using cardiac MR data that I have. And it's not from this thesis. It's sort of a different implementation, but the idea is similar, where it's sort of a multi-scale approach. You sort of solve it at a lower resolution, then bump it up, because higher resolution computations are more costly than lower resolution. So the function call in Python is, so we have rtk.registration.LDDMM, which is our class. So the number of steps is the number of subintervals of 0, 1 in our path of diffeomorphisms. We pass in a regularizer and a similarity meaning distance measure. And then pass in the number of iterations at each resolution, the scaling factors for the resolution, some regularizing smoothing values. What else? Not sure what this does. This basically tells you how close you have to get to the image to be done. This tells you how fast you get there. Then you can do CPU multiprocessing as well if you're into parallel computing. So the sort of basic example here is we're going to take a cube and we're going to register it into a sphere. Now, you may be wondering how that's even possible because a cube has sharp edges and can't be diffeomorphically mapped to a sphere, although we're going to try our best. So yeah, this is a 120 by 120 by 120 shape, which is fairly standard for medical images we encounter. So you can see on the left is our wannabe sphere, and on the right is the actual sphere, and it looks pretty good. I mean, there's these things obviously coming here. I'm going to call them wireframe artifacts, which are pretty much a result of the fact that we can't actually diffeomorphically map a square into a sphere, or square into a circle, cubed sphere, same idea. So this took me about a couple minutes and some change on my laptop CPU with 4 computation threads, which is a little long, but it's totally reasonable, I think. And the cool part is this plot, which I'm just going to let play and you get to be hypnotized by. It's the Jacobian determinant at each point as we progress through the z-slices. So the idea is that we're warping the grid, right? So a good proxy for local volume change is the Jacobian determinant because it's telling you what is the linear scaling factor of each grid point. So you can see here that as you get sort of closer to the center, we're getting really hot, really high values of our Jacobian determinant, meaning we're really changing the volume in the center, which is good, meaning we're doing a large deformation, which is exactly what LDDMM is supposed to do, large deformations. So this is a very good, very promising sign, like, okay, yes, this is doing what we want it to do. So in my world of cardiac imaging, what I want to do is register between cardiac phases. So this is what's called a short axis image, which, so if I'm here, my heart's like here, I'm sort of looking up the heart and slicing it perpendicularly here. So we're sort of seeing a cross section of the heart as we're sort of looking up. So it's a little bit hard to see here, but the phases are slightly different. You can see these sort of circles here, which are actually the blood pool. That is a little bit bigger on this side than it is on this side, and we want to sort of line up to do sort of multi-contrast imaging in particular is the main application. So this is 2D slice 169 by 169, although we can do this in 3D, I just haven't yet. So here's sort of the fixed image again, and here's our difference image. So see here is the higher normalized difference between the fixed and the moving. Again, around this area is where I would expect to see the difference, given that this is a bigger circle than this. Now, after doing the registration, it's definitely a subtle change. There's not a ton of change in our difference image, but it means it's doing something. It's not, the algorithm isn't giving up, which is great, which means there's room for tuning. I guess, yeah, I can show you the Jacobian determinant here, which is taking values between 0.9 and 1.3, which means it's doing a pretty small deformation, but it's doing it in exactly the right areas, which is good. So, and this took me about 10 seconds. And we dropped the mean squared error metric to about 0.9 of its original value, which is cool. But then this means, okay, we can take it further. So first what I want to do is crop into the heart to just get only the relevant part of the image to register. And second is, I think we can change some of the hyperparameters, maybe the threshold, the unit threshold in particular, to get a better registration. And this is actually sort of hot off the press, like I just did this on Friday, but yeah, it works. So you can see here that, so here's the moving image, here's the warped image, which is sort of the registered, and here's the fixed. So you can see that here, this circle got smaller in the warped image and is closer to the fixed image. And the difference image, you can see blue here is high, and the value drops down after the registration. So it's doing a pretty good job, I would think. And then the determinant is, yeah, it's cranking the value up a little bit higher at 1.5. And you can see that's looking pretty good between the two. Maybe this is a little bit over smoothed, but I think it's a really good result, and I'm excited to see what my supervisor and lab mates think. So if you want to code this, I would highly recommend going to my fork of this original GitHub repo, because I edited it for Python 3 and now it actually works. So I don't want you to waste an hour and a half of your time trying to get the original to work when there's a lot of debugging that needs to be done. So with that, I mean, if you want to get in contact with me, you can email me here. Otherwise, I'm happy to take any questions you have.
So thank you, Calder, for giving this talk. Does anyone have questions?
Guess I confused the entire audience then. Fantastic.
It's not often that you end up getting a talk about heart imaging.
Yeah, I mean, that's one of the things of, you know, I'm definitely not the best math student in the department at Chicago because, well, I didn't do a math PhD, but there's still lots of cool applications of powerful math to, well, other places like medical imaging or even econ. So it's like, there's definitely ways to take your math training and put it into a different setting than you would ordinarily be used to.
Okay, so we can end recording now.